In this video we will be solving a problem related to the Brayton Refrigeration Cycle. Got this problem given to us, and in which we have the pressures given to us. We've got temperatures at two states given to us. The isentropic efficiencies are given as well for the compressor and turbine, which means that we will be analyzing the actual cycle, and we have to find out the refrigeration capacity and the coefficient of performance. And we're solving it by air standard analysis, and that means that we need to find out the enthalpies at each state. So the first thing that we would want to do is to make the schematic, which would be a compressor which is connected to a heat exchanger, a condenser, and that's connected to a turbine over here, and then another heat exchanger, which is going to be the evaporator, and the evaporator is connected to the condenser. So we're going to be taking our state 1 at the inlet of the compressor, state 2 over here, 3 at the condenser exit, 4 at the turbine exit. So that's our schematic. The TS diagram associated with this schematic is going to be such that on this TS diagram we're going to have constant pressure lines. So let's say we've got a constant pressure line over here and a constant pressure line up here. So across the compressor the pressure rise takes place, and let's say that state 1 is over here. State 1 to state 2, and because right now first of all we need to look at the isentropic processes across the compressor and the turbine. So 1 to 2 is going to be a straight vertical line. 2 to 3 is then going to be across the condenser, which is going to be a constant pressure process. So an isobaric heat rejection process, because Q dot out we've got over here. We've got work that we're supplying into the compressor over here, which is work done across the compressor. So we've got state 3. State 3 to 4 is going to be across the turbine, where work is being generated across the turbine. It's going to be an isentropic process, which is constant entropy, so it's going to be a vertical line pointed downwards. So it's important to indicate the arrows as well here. And then process 4 to 1 is going to be across the evaporator, where we will have Q dot N or Q dot refrigeration over here, or refrigeration capacity. So 4 to 1 is going to be on this pressure line. So now we can identify the information that is given to us and write it over here. You got this pressure line because it's operating between 5 bars and 20 bars. So pressure over here is 5 bar. I've got 20 bar up here. And so this is P1, which is the same as P4. And up here, this is P2, which is the same as P3. Other than that, we've got temperatures given to us. So we've got air temperature at the compressor inlet given to us. Compressor inlet is 1. So that means I've got T1, which is 7 degrees Celsius. So I convert it into kelvins, and that would be 280 kelvins. Then I've got the air temperature after heat rejection to the surroundings. Heat rejection is taking place up here with the condenser. So after it, that means we're talking about state 3. That's 37 degrees Celsius. And so T3 in kelvins is going to be 310 kelvins. So these are the ideal processes. For the actual processes, we're only going to be considering the non-isentropic effects across the across the compressor and the turbine, because we've got isentropic efficiencies given to us. So that means 1 to 2. This is the ideal process, but the actual process is going to be like this. So 2 dash is going to be here, and then we're going to have 3 2 4 dash over here as the actual process. So we're applying air standard analysis, and what the air standard analysis means is that we will be using the air data table, which is usually available to us in thermodynamic tables. And other than that, we are going to be applying the relative or reference pressure relationships. So the first and foremost thing is that we have to find enthalpies at all the states. So for state 1, the information that is given to us is the temperature, and that is 280 kelvins. And so if we go to the air data table, what we see is that we've got temperature here, and across this we can read enthalpies. So across 280 kelvins, because this is in kelvins, we got enthalpy given to us, which is 280.13 kilojoules per kilogram. And across this we also read this value, which is PR, relative reference pressure, and we write this value as well. So it's 1.0889, and because it's a ratio, so it doesn't have any units, and we pick up these values and we write them down here, that we've got H1 280.13 kilojoules per kilogram, and PR at state 1 is 1.0889. And because the process 1 to 2 is isentropic, so across this process 1 to 2, we can find out the value for PR2, which is going to be the ratio P2 by P1. And this is over here, we've got PR1, it goes on the other side, so it's PR1 here. And P2 we've got 20, and P1 is 5, so it's going to be 20 by 5, which is 4, and multiplied with PR1, which is 1.0889. And you can just evaluate this, and this is going to give us PR2, which is going to be 4.3556. And now what we do is we go back to the table with this value and we interpolate to find out the value of enthalpy at 2. So we take this value, 4.3556, we try to find it down here, and so we go lower, and it's going to be in between these two, 4.3556. So it's somewhere in the middle, I'd say. And across this, we've got enthalpies here. So I'd say that enthalpy is somewhere in the middle as well. So I'll just assume that it's 416 kilojoules per kilogram. So I've got, that means enthalpy at 2, which is approximately equal to 416 kilojoules per kilogram. And now for state 3, so we've got state 2 over here, and for state 3 we've got again, temperature given to us, which is T3 equals 310 Kelvin. And now we do the same thing. We go over here and across 310 kelvins, we look at the enthalpy and we look at the value for PR. So that means we got H3, which is 310.24, and we got PR3, which we just read off the table, which is 1.5546. And now for process 3 to 4, which is the isentropic process, the ideal process, again we evaluate PR4 by using the same relationship. So PR4 by PR3 is going to be equal to P4 by P3. So it's P4 by P3 multiplied by PR3. And now it's inverse, so it's 5 by 20 into PR3, which is 1.5546, and that's going to give us the value of 0.3887. And now that we have this value, we can go back in the table, we can interpolate across this value to see the value of enthalpy at 4. So it's 0.3887, and we see here that it's closer to this value, so enthalpy should be closer to this. I'm just going to assume that it's maybe 208 kilojoules per kilogram. So for state 4, got enthalpy at 4, which is approximately equal to 208 kilojoules per kilogram. So we've got enthalpies at all the states now, but we're not done with finding out the enthalpies, but because we've got this 2' here and 4' here, which are important, that we need to find out. And to do that, we need to use these isentropic efficiencies that are given to us. And for the compressor, we've got the relationship, which is going to be the isentropic efficiency. That's going to be equal to the enthalpies across the isentropic process over here, 1 to 2, and H2- minus H1. So from here, if we simplify it, we're going to find out H2-, and that's going to be 441.88 kilojoules per kilogram. So an important thing to notice is that you could think that how do we figure out if it's ideal by actual or actual by ideal in this equation? Well, it doesn't matter. If you work it out and you find out that H2-, once you found it out, it's smaller than H2, then you're going to be wrong. So H2- is most probably going to be larger than H2, right? So over here, it's going to be up higher, so it should be, and enthalpy is usually increasing as we go up the TS diagram, as we go up vertically, so it should be increasing. So H2- should be a higher value as compared to H2. And just like that, we can go ahead and write down the isentropic efficiency for the turbine. And for the turbine, it's the opposite, it's the other way around. It's going to be H3 minus H4 dash by H3 minus H4, because it's between, the turbine is operating between state 3 and 4. And that's going to give us H4 dash, and that's going to be 226.4 kilojoules per kilogram. Okay, so we've got enthalpies that we needed at all the states now, and we can go ahead and find out the refrigeration capacity first of all. And refrigeration capacity is just this Q dot N over here that you have. So if you go back to the theory, you're going to see that Q dot N, I'll try and write it down here. So Q dot N by M dot, where Q dot N is your refrigeration capacity or your refrigeration effect. And because we don't know what the mass flow rate is, so we just keep it over here, and that's going to be equal to, because it's between state 4 and 1, so it's going to be H1 minus H4 dash, not H4. And then we can evaluate this, and we're going to find out that this is going to be 72.1 kilojoules per kilogram. But we also want to find out what the mass flow of air is per ton of refrigeration, and that means we need to substitute 1 ton over here, and this is going to be equivalent to, 1 ton is equivalent to 14,000 kilojoules per hour. So we just like plug it in here and take M dot onto the other side, bring 72.1 onto this side, and it's gonna be M dot equals 14,000 by 72.1, and once everything gets cancelled out in terms of kilojoules and kilojoules, then we're going to be left with kilogram per hour. It's going to be 194 kilogram per hour, and we can convert that into kilogram per minute or kilogram per second if we want to. It's going to be 3.23 kilogram per minute. So that's the mass flow of air that is needed per 1 ton of refrigeration. And then we can go ahead and find out the coefficient of performance if we wanted to, because coefficient of performance is just a ratio of your refrigeration effect to the work done across the cycle. So it's a ratio of your Q dot N, or we could just divide it by M dot, divided by work done across the cycle, and work done across the cycle is, hang on, I'm running out of space here. So work done across the cycle is work done across the compressor minus work done across the turbine. And we can just substitute the enthalpies here, because Q dot N by M dot is H1 minus H4 dash. And down here, the work done across the compressor is between state 2 and 1 or state 2 dash and 1, so it's H2 dash minus H1 minus, across the turbine we've got state 3 and 4, and this is H3 minus H4 dash. And once we plug in the enthalpies, we're going to find out that the coefficient of performance is really low, because it's just 0.689. So this is how you solve a Brayton refrigeration cycle, by using air standard analysis, by using air data tables, and it's pretty straightforward. You just got to go and see what this reference or relative pressure is. It's just evaluated on the basis of 3 variables, which are entropy at 1 atmospheric pressure and some temperature T, and on the basis of the gas constant as well. So you're still assuming the gas to be an ideal gas, but it's instead of using the relationships of temperature ratios and pressure ratios, you're using the air data table instead.